Okay, in this video for the solar shed, have a look at two or three things. So first I'll have a look at setting up my development environment. So I wanted to be able to code on my Windows machine, but have the actual code being run on my Raspberry Pi. So I got that set up. Then I have a look at the code I wrote, mainly to be able to talk to the renogy, to do the logging, to create a program that runs as I found it's a daemon on Unix, so it can run all the time in the background and control the solar system I've got out there. Then I have a look at the logging function, pulling the logging data off. Look at a few graphs I could do with the logging data. This will give me some ideas for when I put together the Angular client, how I actually want to display the data. And I think that's about it. I was expecting in this video also to get into putting together the Flask base web services for this, but I think that'll take almost another video to get through. So let's have a look at setting up the development environment. So I'll show you the development environment I set up for the Raspberry Pi. I really like using VScode for doing development, so I wanted to have VScode running and be able to manage all the files and development on the Raspberry Pi. Initially I thought I could just install VScode on the Raspberry Pi. It allows you to do that, but performance is really bad for some reason, so I stopped doing that. My next attempt was to just use SMB file sharing to the folders that I'm going to develop in. I could do that with Visual Code again on my Windows development machine and just connect to a SMB folder on the Raspberry Pi. But I couldn't use all the functionality of VS Code. I couldn't do things like bring up the terminal window and run things in VS Code that way. And after a bit more looking around, I found out there's a real solution out there I should have known about. So SSH remote extension for VS Code, or remote development extension, and I'll show you in this video how we use that, is what I used in the end. So that allowed me to connect up via SSH to my Raspberry Pi. Then everything in Visual Studio running on my Windows just looks like I'm running with local files and local environment, but I'm SSHing over to the Raspberry Pi. I could see all my files. I could then use the terminal functionality in Visual Studio Code, and then finally I could also do the normal thing of connecting it up to Git and GitHub in the back end. So I've got a repository out there that syncs to my Raspberry Pi coding. So I think I'm good to go for development, but let's just have a quick run through and have a look at how it was all done. So before doing anything else, I did a update and upgrade on the Raspberry Pi just to make sure all the latest things were there. At the moment, the only big library I'm going to be using, a Python library I'm going to use, is this Pi Modbus for interfacing between the Renogy solar controller and the RS-232 and serial interface on the Raspberry Pi. So just having a look at my Python and pip versions. So I'm up on a fairly latest ones at the moment. And then I'll just do a normal pip install of Pi Modbus. I was thinking of using pip-env, which allows you to have virtual environments and multiple environments on your Raspberry Pi, but that's kind of overkill for a Raspberry Pi. Next up, I just went through, and like I said at the beginning, I decided to use remote development extension in VS Code to SSH connect to the Raspberry Pi. It turned out to be fairly easy to do and certainly adds a lot of functionality, so I installed the extension. I could have a look at my SSH targets. I don't have any at the moment, so I'm going to set one up to my Raspberry Pi that's called Solar. So you just put in the connection information. And the host name is Solar for my Raspberry Pi. I'm going to keep the configuration settings in my local information. I could have connected at this point, but you can also connect from the SSH targets. It's going to ask for a password, or the SSH password, to connect. And then I can open a folder on that Solar SSH connection. And again, it's going to ask for a password to connect to Solar for that particular folder again. And you can see there, now it exposes the files that I already had on that in that Solar directory. And I can also bring up the terminal and just run normal Python programs from the terminal, which is kind of nice. Everything's in one place in the IDE now. And the final thing I want to check on is that I could use GitHub with it. So put some more files out on in that Solar directory. I've got GitHub over it, so I created a GitHub repository, which is a sort of a one-click operation. So I'm just doing a change to some of the code. Now if I look in source control, I can do all the normal things of get comparisons of what the source looked like before and after. I can put comments in. For all the changes I make, that get recorded in Git. And I saved it to Git, and I can also sync the changes up to my GitHub repository. Let's just go have a look in my GitHub repository, just make sure we can see those changes, so we can see the comment about the change there and the actual change in the code. So it looks good. So I'm going to work on the Solar Daemon code, but just before that, have a quick look at the way I set up folders under the Solar folder. So I've got a folder for working programs, for just where I'm playing around with the code, so things you saw in part 2, like testing out the Raspberry Pi to Renogy connection. That code was in the working directory. In this part of the video, I'll look at putting together the Solar Daemon Python application, and that's going to be a daemon application that just runs all the time and watches over the Solar components and turns things on and off and records logs and things like that. Solar www is where I'm going to put together a Flask application that's going to provide some simple web services over access to the Solar functionality. Solar UI, so I'm going to put together a lightweight Angular program that's going to talk to these web services, and that's going to be the primary interface for users who want to see what's happening in the shed. And finally, this directory here called shared, this is where I'm going to put common modules, Python modules, and you'll see for Solar Daemon and Solar www, I've got a couple of modules in line already for that. For Python to be able to see that from the other directories, I'm going to update my Python path. This may not be the best way to do it, but again, because I'm doing all this on a Raspberry Pi and nothing else is going to be running there, it's going to be fairly dedicated. I think I can do it with the Python path share to make sure everything can see that directory. So let's have a look at the Solar Daemon. So this is how the program's going to work at the moment, and probably change as I work on it. So it's going to initialize, it's going to reset the relays out in the shed. It's going to use this file called solarcache.json to persist data that it needs to persist, which is going to be things like runtime settings as well as data that it's collecting all the time, things like relay timeouts and things like that. And it's going to set up this interrupt. So I'm going to have at least one interrupt available where I can interrupt the processing of the Solar Daemon and do things like turn on relays straight away when I request it through a web service. And then we get into the main loop. So this is the piece that's going to be running all the time. Basically, I think it'll be a loop with like a 60-second sleep in it. And then within that loop, if the current hour is changed, then it's going to write out an entry to the Solar with a date in it JSON file, which is going to be a daily log of power generated, power used in the shed, and then it's going to get that data from this in-memory area called running totals, and then it'll reset the running totals each hour. So we'll have one of these JSON files for each day with 24 entries in it. And then in the main loop, so every 60 seconds, it's going to wake up. It's going to get the renogy data. It's going to update the running totals. So the thought is that this is going to be kind of a running average. So I'll just be adding to it and keeping track of how many I've collected over each hour, and then average it to put it into these hourly totals. Then it's going to go out to the solarcache file, which is a JSON file. Like I said, it's just got the runtime parameters and data in it. So it's going to get that. It's going to update any relay timers it needs to. So if I've set a timer for a relay that have expiry dates or expiry times, it'll update those timers, and if there's any relays that are due to be turned off, it'll turn them off. And then based on the running parameters, so there's parameters in there to say what state the battery has to be at for certain things to be turned on. It'll also decide whether a relay should be turned on and off, to turn on things like webcams or do other things to help maintain the power. Then it's going to write out that update data to the solarcache JSON, and this is going to be a locked file because it's going to be shared with web services as well. And then finally there'll be this terminate section. I'm not sure whether I'll ever hit it, because the idea is this is running all the time unless the Raspberry Pi gets turned off. But if we do hit terminate, it'll reset the relays, reset solarcache. Okay, let's go into Visual Studio Code, and again remember it's tied through SSH to the Solar top level directory, and then there you see these subdirectories here. So the first thing I wanted to work on was the renogy interface. I wanted to turn it into a class. So you remember in part 2 I had this renogy test routine. It was just sort of quickly put together to try out Modbus and pull data off the renogy. So I've upgraded that to being an actual class here. So it's in the shared directory. It's called renogy, and the class name is renogy. So it acts more like a class so that I can create an object to use this, and it hides a lot of the Pi bus stuff and some of the manipulation of the data. So it basically starts up, goes into init, clears the variables, starts up the Modbus interface, and then calls refresh, and refresh pulls the data from the Renogy Solar controller, sets the scales to ones I want to use, does some manipulation of the data, and then closes down the Modbus interface, and that's all nicely wrapped up there. So instead of having my old Renogy test here where everything that was together, this is kind of how you'd use this Renogy class. So you do a from Renogy import the Renogy class. So Renogy is the module, and the capital R Renogy is the class name. Then all you do is initialize an object. In this case I called it R, with the Renogy class, and remember init gets the initial values, so R will have all the initial values in there, and you can see here's where I print out those initial values just to test it. So let's try running it, make sure it all works. So for my terminal I can do a Python 3, and this one's called renogy class test, and you see it all worked. It must have retrieved the data from the Renogy and printed it out. Okay, next shared module is the solarcache one, and this manages the solarcache JSON file. So a few different processes will be wanting to read and write from that file. So that manages things like the properties of that file, and reading and writing to that file. So to give an example of using it is I import solarcache class, create a new instance of solarcache class, and then print out the contents of the solarcache class. And at the moment I do have a solarcache JSON file out there with this information in it. So let's try running that. So basically print it out as a Python dictionary, the contents of that file, and you can do changes to this and again, this is JSON on the file. Let's save that, run it again, and now it picked up the contents of that file and put it in. Okay, next class and module I put together was this solar relay controller. So again, the solar daemon and the solar www web services are both going to use the relays. So this is what the class looks like. Again, init hides all this GPIO stuff by putting it in a separate class. And I've got 4 functions: one to turn the webcam on, one to turn the webcam off, and one to turn the rig on, one to turn the rig off. So as well as flipping the GPIO pins the correct way to turn the relays on and off, it also writes out the state and sets up expiry times for the 2 relays in the solarcache JSON file by using the solarcache class. And let's just test it's going to work. So first we'll have a look at how much power we're drawing out in the shed. So at the moment we're drawing 1.29 watts. So let me go out to my tester routine and turn the webcam on, and we'll run that, and let's have a look at the solarcache JSON, and we can see here that the webcam value is true, and it's got an expiry date which should be 60 minutes in the future. And also if I look at the power being drawn out in the shed, it's now shot up to 2.6 watts, which is what you get when you have the webcam going. So this is all working. Okay, I think this is the last module I'm working on for getting back to the solar daemon. So this one's called solarlogger. So this is the module that helps with writing out the hourly data from the solar controller. So gathering the data, writing it out every hour to the log file. So each log file contains a day's worth of data, and the function that does that is in the solarlogger class called write data. And I just pass over at the moment the battery capacity, the solar power coming in, and the output power going out of the controller. And this writes out a file that looks like this. So it's just a tab delimited file and has up to 24 entries each day before it rolls over to the next day's tab file. The other thing this class does is the get log data. So I can just put a range of time, so from a beginning time up to either the current time if I leave it out, or any specific end time, and it brings back one big tab delimited string that has all the data between those dates and times, and that's what the code that does that. So let's have a look at it running it again. So we're going to use this solar logger test, and I'll just run that. So you see it's run. It's actually this print statement here printed out the values between these 2 times. So those are epoch times, seconds since the Unix started the Unix epoch. So it's picked up two rows, but it'll go across the separate log files and pull them back, but it's all kind of invisible by having it in this class. And I also wrote out a new data record, this write data, 50% power in the battery, 9 amp hours of power coming in, 8 going out. And let's have a look. So there's the entry in today's tab history file. Okay, this is the first cut of the solar daemon program. So this is the program that runs in the background, just keeps an eye on things and does the logging. So this first cut, I really just wanted it to do the logging, so I can get some logging going, so I can watch the status of my solar panels and things in the shed for a while I work on the second half, which is to add the power rules. So let's have a look at the first cut of this. So I imported the various modules I've created earlier in this video. That made it a lot easier. It sort of took away all the complicated stuff. So let's have a look at the program. So you see there's not a lot of code. So first thing I do is call the main routine. And the main routine calls initialize down here, and then it goes into the continuous loop. So while true, it's going to keep comparing the last main loop time against the current time. It's going to compare the hours. So if the hour changes, then it calls write log. So this is the part where every hour it goes and checks and writes out a log record if the hour is a new hour with all the details from the previous hour. If it's not a new hour, then it does an update state, and then it goes to sleep for 60 seconds. And let's have a look at initialize. Initialize just does a print statement, so I know it's gone through there, and uses the solar relay module to turn the webcam off and the rig off. So that just gets us to our initial state. So let's have a look at write log. So this happens every hour. So it calls out that it's using these global variables. I've got a print statement so I can keep track of things. Brings in the solarlogger module from earlier. If the loop count's greater than 0, this is just to make sure we don't have to divide by 0 errors, but it should always be greater than 0 because it's been looping for 50 or 60 times before it gets here. It calls the write data function in the logger and writes out the battery capacity, the solar power, and the power output averages over the last hour, and it just reinitializes all those values and sets the last main loop time to the current time. And the other thing that's happening is every 60 seconds it's doing this update state. We saw it in this main loop here, and the update state again calls out the global variables I'm using. If the loop count's greater than 0, again, so I don't avoid dividing by 0. That's just as some print statements in there, so I know how things are going. Then it'll increment loop count by 1 and add the renogy data to the running totals here, and that's it. At the moment I've got this running, and we can see it here. So I use this command to run it, so it runs in the background, so I don't get I can't run it, don't get a command line that's running continuously. So there's no hup command, is no hang up, which means if I exit this SSH session, it'll keep running. I'm telling it to run Python 3 with the -u option. So this is saying don't buffer the output. So as it does these print statements to stand it out, they'll be written immediately to the file, and we'll see why we do this. Then I'm running the solardaemon program. I'm piping the output to solardaemon process log, which is being created here. I'm using the AND statement, so it runs in the background. So the result of this is it runs continuously in the background. It's not tied to my session, and if I want to see it running, I can use this processor command with greep, and I can see there it is running in the session number. So if I need to kill it, I can kill it with the session number. So like I said, the print statements are being piped out to this file here. So it's been running for a while, but it's sort of telling us what's happening. So it does one of these when it changes the hour, and then every 60 seconds it's writing out the data that it's adding to the running totals. And that's why I'm using the -u option, so it writes to this file continuously so I can see the progress as it runs. And like we saw earlier, it's using the solar logger to write out these daily tab files, and this is kind of what it looks like at the moment. So every hour it's putting adding an entry to the file for that day. Okay, this is my first cut at graphing the data. So in this case I just brought it into Excel to see what the main data looks like. So you see the lines down here, so this orange line shows the solar watts per hour being produced, and this is just over a span of 1 day, so you see it bounce up in the morning where a lot of solar energy is being produced and my panel's pointing in the right direction. This dotted line is the load or the output from the solar controller, how much energy is being used, and that's running around 2 to 4 watt hours during the day. You can see it drops during the night because that's when I have the camera turned off, and then in the morning the camera starts up again. You see the consumption goes up. So overnight it's really just powering the Raspberry Pi. And this dotted blue line is the battery capacity, so as a percentage. So use this right hand scale here, so starts the day, or starts around 100, drops to about 75% battery capacity before the sun comes up in the morning, then rises up again. So some little things I noticed in here. So before the webcam's turned off at night, it switches over to using the infrared lighting on the camera. So there's a bounce here because that uses a lot of power. So you see just before the camera turns off, there's a bounce in power usage and also a dip in the battery capacity. And here you see where the webcam's actually turned off, so it restores a little bit of battery capacity at that point. In the morning you can see when it turns on the webcam, so basically once it starts seeing the solar panel producing power, it turns on the webcam again. You see the power consumption goes up, and you see the solar panels producing power. Now something interesting, I thought I had lots of power up till about 2 o'clock during the day, but you see the renogy's reporting that the power starts dropping off, or the solar power being produced starts dropping off about 11 o'clock or so. So I put my data logger out there, and this just shows you a profile of how much power is being produced, or how much power the sun's providing during those morning hours. So you see there's pretty much maximum power is being produced all the way up to about 12 p.m. But you see the renogy's only using that power up till about 10 a.m. I think what's happening is the battery becomes fully recharged here, and I also saw that the charging mode on the renogy changed from boost to float at this point, where it's just keeping the power maintained at this point. So I think the renogy's reporting on how much power is actually being used from the solar panel rather than how much they're producing. So you see it's dropping down here. So that's interesting. There's 1 day's worth. Let's just have a look at the same thing over multiple days. Hey, this is a few days later. So I want to get the output from my logging for the last few days. So I'm going to run the solar logger test, which just pulls a few days data. So here's, you see all the data. I've actually added a whole bunch more columns being reported on, so the percentage time spent in the different charging modes each hour is included now. So let me grab all that, and I'm going to go back over to Notepad, paste it in there, just save this as a file. So I'm saving this as data CSV. Now I'm going to go to Excel and use the data function to import that file I just made, which is out in temp. And I'm going to say it's comma separated. It looks good, so let me load all that in. So there I have all my data. I'm going to get rid of this bulk column. And now I should be able to graph all this. I'll just grab all the data that I want to graph. I don't want to go... Yeah, I only want to go up to the float point. And let's do a insert. I'll just insert a simple chart. And I'll just use the dual axis, so these things that are measured in 100%, I'll put it on the secondary axis, and then we'll have a look at it. Okay, that looks good, and I'm just going to change the mode mode display to be dots, so it doesn't so you can still see the main things that are going on. And the nice thing about doing this in Excel is I can work out what I want before I start graphing these things in Angular. So this is almost 3 days. So starts about 1 o'clock on the first day, and it's ending about 10 o'clock on the third day. So almost 3 days. So up here you can see the battery percentage, this blue line, as it changes. You can see here how the different charging modes are happening. So this second day might be the best one to see. So overnight there's no charging, no charge mode, which you'd expect if there's no power coming into the solar controller. Then it goes into boost mode here with the dotted blue line, and then once the battery gets to 100%, it's going into float mode, so it's just maintaining the battery voltage. And then once the power coming into the solar controller drops enough, then it's going back to boost mode. While it's still got some power off the solar controller, then it drops right off. You see here the spike at the end of each day as the controller's still running the webcam, but the webcam's flipped over and automatically turned on its infrared lighting, so it uses a lot more power, and then soon after that it drops way down when the webcam's turned off. A couple of other things I did to the Solar Daemon. One, I changed its name to Solardaemon. I found out Daemon's a better name for what you call services in Unix. And then I added in the power rules, so the rules about how the solar controller should be turning things on and off depending on different power conditions. So the first set was for the webcam, so the default state of the webcam is to be on, so I set the webcam rule to true. I go down here, if I've got enough data in the runtime details, then if the battery capacity has fallen below what I've set as the minimum battery capacity, then it'll turn the webcam off. Same thing if I say don't run the webcam at night and the solar power indicator indicates that there's no power being coming from the solar panel, then it turns off the webcam as well. And then this rule here for when to force the webcam to be turned off, so I can set a time between 6 PM and 6 AM, and this will turn off the webcam if it's running it at those times, if I have this parameter set. And the final one in here is if I've manually called the solar relay controller and forced the webcam on, it'll stay on no matter what the rules are for predefined amount of time until the expiry time comes up. So this is just seeing whether it needs to keep forcing the webcam to be on, or if it reaches that expiry time, then it sets the expiry value to none, which means it will no longer go through this logic to force the webcam on. And then finally down here it'll set the webcam power based on whether it needs to change the setting depending on whether the webcam's already turned on and off. If it's off and it's been told to turn on, then it'll turn it on. If it's on and it's been told to turn off, then it'll turn it off. And I've got a similar rule for the rig as well. So the rig doesn't have a lot of rules other than the one where I can set it to stay on for X amount of time and then it'll turn itself off. So that's about it for this video. I was going to try and fit in the Flask based web services as well, but that's going to take almost another video to get fit in, so that's it for this one.